All right, y'all. 9:30. Everyone hear me okay? Good? Thumbs up? Awesome. Sweet. So, welcome bright and early, my chipper darlings, to the first Tuesday session. Today we're going to be talking about performance. Performance in hybrid applications, but a lot of this is equally applicable to performance in your mobile and web applications. So if you got anything that you like, take a picture of it, post it on Twitter, hashtag perf matters, because, hey man, perf matters, right? Like I said, this is really fundamentally a talk about HTML performance. And so it applies in all sorts of different kind of locations and venues. A lot of the same lessons that we learn here will even apply to desktop applications. But all that processing power that we typically find in desktop applications, it really gets magnified when it becomes constrained in mobile apps. And so that's why perf for mobile becomes so critically important, so important for the user experience. Doesn't want to advance. All right, so about 30% of today's talk is really going to be focused on hybrid apps, and the rest of it will be all across the board for mobile, web, and for hybrid. But just to make sure that we set a baseline here, let's do kind of like a big hearty yar if you know what a hybrid application is. Yar, right? Okay, cool. Those of you that got no freaking clue what a hybrid application is, say, oh, really? Oh, that's great. That's fantastic. All right, sweet. So I don't have to do a whole lot of level setting, but here's how it basically works. A hybrid application, otherwise usually known as PhoneGap or Cordova, lives inside of a web view. That web view lives inside of a native container. And then other than that, it's pretty much a web application, right? The only difference is that every time that you want to access native APIs, you've got to make a call into a plugin, which then makes an asynchronous call between the web view and the native code. So let's say that you want to access the camera or the accelerometer or the address book. You got to make that asynchronous call across the bridge. Once you've made the asynchronous call, it will return back a result from the native API. And so you've got to do this little dance every time that you want to actually access a native API. But otherwise, it's the same HTML, CSS, JavaScript, web app that we all know and love and is great. So I personally, I work inside of tools for building hybrid applications, and so I love them, but I hear a lot of kind of chitter chatter and misconceptions in the marketplace that say that, hey, they're kind of slow, they're kind of sluggish, they don't really kind of pass the test. And so my goal today is to hopefully dispel at least some of those misconceptions, or at the very least, equip you with knowledge based upon scientific facts, actual experiments that we conducted that shows, what is the truth of the matter performance? Where are their liabilities? Where are their constraints? How do you troubleshoot some of those constraints so that you can fine-tune and optimize your application for the best performance possible? So in order for us to do that, we all need to kind of agree on a common definition for what it actually means to be fast and responsive. Because we can measure milliseconds until the cows come home, but in the end, just controlling for milliseconds themselves isn't enough. You actually need to take into consideration the context for those measurements and what they actually kind of mean in terms of user perception. So just so that we've got a common kind of understanding here, let's think about it this way. So that says interaction classes. You're missing like the last 15 pixels on the left-hand side. But so on the left-hand side, 17 milliseconds, everything that is fluid. This is not about user interaction with your application. This is about the perception of it. If you do the math, that 17 milliseconds kind of adds up to be 60 frames per second. This is what it means for the app to look like it's fluid, like there's no jitteriness or there's no kind of tearing in the movement on the app. Just beyond that, instantaneous. So instantaneous, this is actually where we get into real user interactions. This is when I click on an object and I drag it with my finger. Does that object actually stay with my finger? When I click on the button, does it immediately change color or do the pulse that it's supposed to do? Next up, that which is fast. This is for sort of macro level navigation or large changes to your UI where maybe you are changing views or you are loading up a new photo, that kind of thing. Beyond that, everything above 250 milliseconds, that's kind of the dragons lie here kind of area. This is the space where if you've got a delay that lasts that long, okay, brother, you got problems, but maybe you can solve those problems by throwing up a little spinner or something like that, and that'll give the user something to do to know that, hey, we're working in the background. Today, what we're really going to focus on is everything on that far left-hand side, because frankly, there's very little question that HTML, CSS, JavaScript, web technologies are able to keep up with any other language when it comes to things right of that. We care about really kind of narrowing in and optimizing for that fluid and instantaneous interaction. So everything that you're going to see today is the result of a series of experiments that me and my team conducted over the course of about 3 months. And in order to do this, we basically took a look at kind of what was being done out there by the common Joe Schmo developer just kind of doing his job every day in the small design agency or in the enterprise or wherever it is. And we took a look at those patterns. And then we compared those patterns up against what was happening kind of in the big frameworks like the Ionics of the world and the Famouses of the world and the WinJSs of the world, as long as that's a thing. And then we kind of said, all right, what's the difference between how these guys put their applications together, and does it have a real difference when it comes to performance? Spoiler alert, it does. That's why we use those frameworks, because they've done all the work for us. And in order to do this, to make those comparisons between, Joe Schmo and the kind of the best of the best of the best when it comes to JavaScript, HTML, CSS developers, we compared them against 3 devices. Now, these are not best-in-class devices. These are not the best devices in the world, but that was intentful. That was purposeful, because we wanted to compare performance on kind of, the device that maybe your mom would have, right? This is so that the everyday person actually knows what it feels like, and that's where we did our actual measurements. We ended up coming up with 6 different categories of kind of areas where you can make improvements, or you can at least have some awareness that there might be some constraints that you didn't know about before. Web view, document object model, images, lots of good stuff. We'll go into each one of these in detail. All right, so let's start with the stuff that really only applies to kind of hybrid applications. Like I said, the first part of this talk will be just hybrid, then we'll expand out to include hybrid and mobile web. And hybrid applications, you have the unique problem of having that web view, that place where you've actually got to span the bridge between native, the code that lives inside of your web view and the native code itself. And what really makes kind of that kind of barrier unique is that you've got to make this asynchronous call every time that you want to call an API. You've also, lordy be, you got to spin up a browser when it happens. You got to spin up a web view. So one of the first places where we thought that there might be some problems was just the fact that you've got to spin up a browser. And we said, you know what? That could very well affect startup time. That sounds reasonable, right? Startup time, you got to spin up a browser, got to spin up a native app. So here's what we did. We took a very kind of like an empty shell of an app, started with a native application, just a simple hello world app, doesn't do anything. And we said, all right, what's the startup time for a plain old native Java app for Android, Objective-C for iOS, C# for Windows? And we measured startup time. Okay, actually we measured memory. And sorry, I got my startup time and my memory one confused. We measured memory of that native application. Okay, that's what a native one is. Then we said, okay, what is it to start up just a browser on those same devices? All right, it stands to reason that from there, the actual kind of memory consumption for that particular, for a hybrid app would be a native app plus a browser, right? Memory footprint of the two, A plus B equals C, because it's a hybrid app is a native app with a web view inside of it. Holy moly, that is not the truth, yo. There is big difference, especially in the Android case, where there's a lot more memory being consumed by a hybrid application compared to a native plus a browser. Now the rest of them actually look pretty rosy. In the iOS case, the hybrid app, it's almost the same as spinning up a browser. That's good. In a Windows Store and a Windows Phone, actually in a Windows Store application, because you're not having to spin up a browser, little known fact, you can run a JavaScript application natively in Windows 8 and Windows 10. You don't actually have to spin up the web view, and so you benefit tremendously from memory footprint. But Android, that World Trade Center tower that's right there, too soon? Keep that in mind, right? Remember that guy. Remember how big that memory footprint is later, because that's going to kind of play back to us later on. Okay, yeah. Windows Store, the native application there? That is a really, really good question. So the truth of the matter is that I suspect, I could be wrong, in our methodology, it's quite possible that we were using a C# XAML application for the Windows Store one, and then for our hybrid app, we were spinning up a JavaScript application, because the vast majority of the native apps in the Windows Store are XAML applications. It's the difference in the memory footprint between the C# XAML runtime and the JavaScript runtime. Make sense? Yeah. I'm sorry, different what? Yeah, exactly. So like, from one to the other, and the performance debt that you pay or tax that you pay for each platform is going to be a little bit different, because each platform has its own characteristics, its own rendering engine, its own runtime, all that good kind of stuff. Okay, so now we're going to get to startup time. I promised startup time from the beginning. Let's get to that. So memory, great, cool. That gives us something to measure, but it's not necessarily something we can see, something that impacts performance or that feels like performance. So here's what we did. We took kind of a slow motion camera. In fact, it was an iPhone slow motion camera. And we measured the startup time for each of the applications. So what you see here are a bunch of frames from the startup time. And then we were able to count the frames. And because each frame equals 4 milliseconds, we could count from, and here on the left-hand side, you can see us tapping it. It's a little bit hard to see in this on this projector, but there's like a faint little glow around the icon, and on the right-hand side, you start to see a little bit of ghosting. You can see it with the clock up on the top. That's the app actually starting to kick up and launch, right? So that's how we measured startup time, from initial click to app actually kind of launching up. And we said, all right, what does startup time look like between these? Now, remember how Android had a really big memory footprint for the hybrid application compared to the native application? You're seeing that manifesting right there on the two left ones. See how large that the green bar is? So memory footprint seems to have a high correlation with performance here. And we're going to see that theme repeat throughout the day. iOS, we've actually kind of got a bit of an oddity here where the iOS native bar is higher than the hybrid bar. I want to put an asterisk next to that one because, like I said, we use the default Hello World app. And the default app, when you just do file new kind of thing, has embedded in it a 500 millisecond delay. That's just part of the default configuration. And so my bet is that if we actually modified that default configuration, we would get it down. But our intent was to demonstrate the out-of-the-box experience for kind of all of these applications. And then it's also worth noting that for each of these, you see Android cold and Android warm, iOS cold and iOS warm, Windows Phone cold and Windows Phone warm. The difference between cold and warm here, cold was that we shut the phone down completely, started it up, and then immediately launched our application. Warm, in this case, was that we shut our phone down, started it up, launched the application, closed the application, and then started the application again. And so there were kind of performance optimizations that the individual sort of OS makers, you know, the Apples and the Windows and the Googles of the world, actually baked into it. Yeah, I got a question over here. Yeah. That's why I believe that the performance optimization that they're making there, and this is where I admit we need to do a little bit more research to better understand it. I believe that you don't actually pay that for coming out of suspension, and that's what's going on. So I will caveat here that more research necessary. All right, so big takeaway here: memory footprint makes a difference. Startup time, and we'll see it elsewhere. But you know, if we're really talking about what's the tax that you pay for being a hybrid application, I think we can also take away from this, with the exception of Android, there's not a lot of a tax that you pay for building using web technologies, at least as far as startup time goes. Okay, so we talked about having to traverse that web view in order to access native device capabilities like the camera, the address book, the accelerometer. So let's take a closer look at what that actually means and what tax we pay there for being in a web view. So here's what we did. We created a simple Cordova plugin. And this plugin, its only job in this big wide world, its only job was to accept long strings of content and return them back. In other words, we just took a small little data size, pushed that over the web view and got it back, and then we gradually grew it. And what you'll see is that the progression is relatively linear. So on the y-axis, we've got time. On the x-axis, we have data size. And you'll see you got a nice linear progression. As the data gets larger, the time goes up. But what I want to call your attention to here is that a decent sized photo to come out of any kind of modern phones like the iPhone 6 or any of the new Nexuses, right? It's in that kind of 10,000 range in terms of file size. So in order for you to return back a relatively large 10 megabyte image, you're looking at 300 to 400 milliseconds. So that's returning back like a 10 megabyte image. If you're actually kind of traversing that web view to make a call to the accelerometer, what is that? How many bytes is that? Like, 10 bytes? I don't know. It's tiny. It's an X and a Y coordinate. If you're doing it to access the address book, right? A little contact card that's maybe 10K, I don't know, something like that. You're down in the instantaneous to fast range, and that's for major API calls. So the takeaway, at least that I got out of this, is that the tax that you pay for traversing the web view and actually kind of accessing those native APIs, it's a pretty low tax. It's not zero, but it's a fairly low tax. An interesting point to make here, you guys see kind of along the bottom here, there's that orange bar. That orange bar represents Windows Phone using JavaScript. That's because, again, within a Windows 8 and a Windows 10 application, because JavaScript can run natively, you don't have to traverse the web view. Therefore, there's no tax to be paid for moving in between kind of your JavaScript code and your native APIs, because those native APIs are called directly from the JavaScript. No tax to pay. I had a question over here. So the elements were, it was strings was the object, and each of the strings, let's see here, what did he use for it? Okay, it was arrays of strings, that's what it was, and each of them was a word. So we just didn't make the translation to file size. I mean, you're totally right. It would probably be a little bit more easier to grok, just translating it to megabytes or kilobytes kind of thing. Yeah. So it roughly ended up translating to a 1-to-1 between kilobytes and array or objects. But that's a really great question. Okay, cool. All right, so bridging the web view, hey, it's pretty fast. It takes time, it's not zero, but you can get across pretty quickly. All right. So I said that about 20–30% of the talk would really be about hybrid apps. The rest of the talk, everything that you hear from here on out, this is going to apply equally well to web applications on mobile devices. So if that's what you care about, great, listen up. The DOM, frankly, this is where we see, this is where you really incur the biggest debts when it comes to performance. And it's kind of no mystery here that that's the case. Everybody knows what I mean. We're at an HTML conference. Everyone knows what I mean when I say the DOM. So from here on out, I'm going to take you through a couple of experiments. And in these, we're actually going to be using primarily the Chrome dev tools to debug what's actually going on from a perf perspective for each of these. So this first one, we're going to take a look at what it actually means. Let's actually blow this guy up. We're going to take a look at what it actually means to kind of work with a simple DOM versus a complex DOM. And in the context of these experiments, we've conducted all of these tens of thousands of times to get a good kind of baseline or a high degree of confidence in what was actually going on. You're just going to see one instance of these experiments, but it's a representative of the test that we did. So I'm going to, in this particular case, what we're doing is I'm deploying to a Nexus 7. I happen to be kind of projecting it onto my desktop using an application called MobaZen, but it's an actual kind of running on the mobile application. I'm not running this on my desktop. These are not the desktop performance stats. And what I'm doing here, and I'm actually going to pause it so we can read it and see what's going on. Each time I click one of these buttons, and I apologize that they're a little bit difficult to read, projector and all, each one of these buttons is creating and destroying a DOM node, essentially. And it's not just a single DOM node. We've got different ways of doing it. We've got a simple DOM node, which is just a flat list of divs. Then we've got a complex DOM node, which is a deeply nested list of divs, kind of randomly nested, but this actually doing different and varying numbers of objects, of elements. And then we're measuring how long it takes to create and destroy them. And this shouldn't come as too much of a surprise. As we create and destroy them, the simple DOM takes considerably less time to create and destroy. The complex DOM takes considerably more time to create and destroy. More elements, more time. That makes sense. But we also take different approaches to creating and destroying those objects. In some cases, we are using just a blunt inner HTML to inject them as a string. In another case, we're actually using a document fragment to build the DOM out, or build a DOM fragment outside of the DOM and then inject it wholesale. And in the last one, we are kind of using a create object insert element. I'm going to back up a little bit so we can see the numbers. Here we are. In the last one, we're using a create object and inserting each object one at a time, each DOM node one at a time. And what's important to note here, hopefully I can get it to the right spot where I'm highlighting. Here we are. So via inner HTML, that's injecting via the string, we've got a median of 0.05, let's see if that's 0.0, so that translates to 0.05 milliseconds, I believe, which is not a big number. But on the simple DOM, we've got 0.02 milliseconds, so about half the time to kind of just inject a simple DOM versus a complex one. Now, I know those numbers are super, super small, but they're going to multiply out. As we kind of get more and more complex with our application, the number of elements can dramatically start to drag at it and tear down at it. I think I had a question in the back. Yeah, unfortunately, it's a YouTube thing, so I can't actually zoom in on this one. So, big takeaway for this one, and I think this one isn't too surprising, is that reducing your element count dramatically can improve the performance of your application. It was by a factor of about twofold. But there's some kind of unusual ways that this ends up happening, and this is where I want you guys to kind of step back and think about what it means to build for performance versus what it means to build for maintainable code. So what we're looking at here is just like a dumb, simple set of HTML, this is like something that we would all kind of, write in our sleep, right? Doesn't look too complicated, but if you actually wanted to optimize for performance, you might do some wacky things. You might actually remove a lot of those elements. In this case, we actually reduced the element count by about 30% by taking and using kind of on-click events on our list items rather than adding in an extra element for the anchor tag. All right, so building for performance, not necessarily the same thing as building for maintainability or code legibility, right? You're going to make some strange decisions when you optimize for performance. All right, so let's take a look at another one. This one's kind of Fastlyst scrolling, and this is where that kind of number of elements in the DOM actually kind of starts to make sense and start to have some kind of real feel to it. When you've got a long list, and think here of thousands of elements, right? And you're doing fast scrolling along that. The amount of memory that each of those elements occupy is relatively, like, as it gets larger, it starts to increase. And that, as we saw back with the startup time, starts to kind of drag at your performance. So here's what we're going to do. In this particular case, we've got two applications. One of them has thousands of elements. Bring this guy up. One of these guys has thousands of elements, and we've made no effort to optimize in terms of minimizing the number of elements that are loaded at the time. They're all just loaded all at once, one big long list. And as we scroll down this list, what you're going to see is I call it tearing. I think a lot of people probably know what I mean by that. It's where the objects themselves stop appearing, and you start to see kind of like a white kind of screen, or you start to see that they disappear. Yeah, here, see? That's not the application crashing or anything like that. As I'm scrolling here, the elements are just disappearing because the runtime can't keep up with all of the objects that are on the page. Too many objects, too much to process. The UI thread can't keep up with it, and so it just decides not to display anything. And then when the scrolling is completed and the UI thread can catch up, then it just kind of displays everything at once. So now, we're actually going to take advantage of that principle that simple DOMs occupy less memory, improve the performance, and introduce virtualization. Virtualization basically is a kind of a methodology, and this is baked into a lot of the major frameworks, where you only load those objects that are maybe 2 or 3 screens before or after you in the visible view. Everything else is removed from the DOM, maybe just kind of held in JavaScript kind of memory land, and it's injected back into the DOM when it's necessary. And look at this. As I'm scrolling here, and I'm scrolling pretty gosh darn fast, all of the objects are still visible. Occasionally, you start to see those little gray boxes. So that's just a little trick that you guys probably have seen this in something like Facebook before, right? Where in Facebook, you start scrolling through your news feed really quick, and you just you see a placeholder for content before it actually loads in the content. Same concept here, but at least you haven't lost the entire UI. You haven't lost the entire view, and you've got a placeholder in there so that you know that scrolling is happening. So from a perception standpoint, this feels a lot more fluid. This feels a lot more kind of intact. Yeah?
Short question. You said you are adding, and I presume also removing the elements on the fly with virtualization.
Correct.
I read before that the general way to approach this is to recycle the code element, thereby just set the new text value, set the new image source element.
Yeah. So I have not done a comparison of recycling versus creating a new and injecting. It makes absolute sense, though, based upon, let me put it this way, I've not done controlled experiments, but I do know that the act of creating an object takes time, whereas changing attributes takes considerably less time. I mean, this is the whole principle that React uses, right? It's really trying to make as few DOM mutations as possible in order to kind of achieve the new layout, right? So it makes total sense that is how it would, that is the best practice there. I just haven't done a controlled experiment to see what the actual impact is.
I would guess, especially if your list items are all the same layout, it really makes sense to change values.
Totally agree. And virtualization, frankly, is one of those things where rolling your own virtualization, like, it's kind of a solved problem by the majority of frameworks that are out there. And so I would tend to rely on frameworks like React to handle that for me. In that particular case, I was using a WinJS one, not because WinJS is like the bee's knees or anything, but it turns out that their virtualization for lists is really, really good. It's one of those things that they really nailed. Lots of things they didn't nail, but that's one of the ones that they did. All right. Uh-oh, we got off of our slide here. All right, back from here. Cool. So I'm going to keep on using memory as a touchstone here because I think it's a good proxy for performance. The virtualized list on the left-hand side uses, what is that, 1/4 of the memory of the non-virtualized list. Again, memory itself is not a representation of performance, but I think it's a good proxy here, and so super helpful. Takeaway, use virtualization. It's your friend. All right, images, another good category of things to look at. So I don't know about you guys, but I have come to rely on CSS gradients an awful lot. It makes for better kind of responsive kind of design. It ends up kind of saving me from kind of creating 1 by 1 pixel kind of tiling images. But again, if you are optimizing for performance, there may be some times that you make different decisions than you would for maintainability or legibility. And gradients happens to be one of those places again. So here's what we did. We ran a comparison of what it is to use a CSS gradient versus an image gradient. Let's make this guy big for us here. All right. So in one of these, I've got an object that's using just a typical run-of-the-mill radial gradient. And in the other one, I've got an image that's using kind of almost the exact same gradient, as close as we could get it. But this time using an image and animating it. For this one, I'm going to bring up the Chrome tools. And I'm going to use the Chrome tools to measure my frames per second. And does everyone here know how to kind of measure frames per second using Chrome Dev Tools? Nodding, I hope so, good. For those of you that haven't used it before, basic idea is that you want the bars to be really low, really high is bad, right? Or actually, excuse me, really high is good, really low is bad, because you want the frames per second. So, oops, let's get back here to it. Yoink. All right. So, as I'm animating the CSS, look how many frames per second. It's kind of hard to see there, but I'm actually getting for the CSS, I'm getting like 30 frames per second. For the image itself, I'm getting something closer to 60 frames per second as I animate it. Why is that? Well, I haven't kind of like looked under the hood and talked to the guys at Google to figure it out, but here's what I think is happening. When I'm animating the CSS gradient, it's got to recreate that bitmap every time it moves, you know, a pixel over or anything like that.
How many times have you heard
Whoops.
you should always use CSS animations?
We just got a little extra lesson there from folks. So it always has to recreate that bitmap image. Whereas when I'm animating an image itself, the image is already there in memory. It's already knows what that object looks like. It is a static image. It doesn't have to recreate it. So kind of when you are working with performance, when you're fine-tuning for better performance, using an image will often give you kind of a better, kind of more fluid, whether it's an animation or occupying less memory, it's going to be a better choice. So use images. There's a bad, you know, I feel strange, I feel weird doing this, feel a little icky, but bad. Gradients when optimizing for performance, maybe not your friend. Oddly enough, good gradients are actually kind of as an image can be good here. Let's talk about garbage collection. Everybody loves the garbage collector, right? Takes away your dirty stuff, takes away all the garbage, but browsers have had a long time to optimize for garbage collection. They're pretty good at it. We don't really, as JavaScript developers, have to think about it very much. But there are times when you can actually code your way into a place where the browser's not so good at garbage collection. And as we saw before, memory being a good proxy for performance, if you're not having kind of all of your kind of unused objects cleaned up for you, that can pile up over time. And I don't know about you guys, but my phone, I don't restart it very often. I don't actually fully close apps very often. And so if days, weeks, or months go by before I've actually closed my application and therefore purged memory, then that memory will pile up over time, and that will have a negative impact as the days and weeks go by on my overall application performance. All right, so here's what we're going to do with this one. In this particular demo, we've got an application that this one is creating. Let's see here. We're creating an object. We're adding in an event listener, and then here's what we're doing. After we've added that event listener, then we're just totally destroying the object by setting enter HTML equal to blank. In other words, our event listener is left kind of still in memory, still hanging around, but the object is gone. It is an orphaned event handler. Does that make sense? Yeah? And what we're going to do is we're going to just kind of still create and destroy that object many, many times. What I want you to do is I want you to look on the left-hand side in the Chrome DevTools. You see that ramp that's steadily growing larger and larger and larger? It's like the fourth row down on the thing. That ramp is your memory growing. That is like Black Death for an app. That's your garbage collector, completely unable to remove all of those event handlers, memory growing over time, and eventually, if you have a hybrid application, it won't necessarily bring down the native app, but it will bring down. Ooh, hello. I'm just going to mute that. That will actually crash your browser or your web view within the native application. And that's icky. Nobody wants that. So, lesson here, like, clean up after yourself. It's just like your mom always told you, right? Like, clean up after yourself. Go pick up your garbage, right? If you've got an event handler that you're using, don't just destroy the object willy-nilly. Actually spend the time to responsibly remove the event handler, responsibly destroy the element, rather than just kind of setting enter HTML to blank. All right. But there's another place this happens. It's not really just about kind of destroying your kind of orphaned objects. It's also about, or your orphaned event handlers. It's also about minimizing the number of event handlers that you've got hanging around. Every single one of your event handlers and your functions that's hanging on the DOM, that occupies memory. By occupying memory, drags you down from a performance perspective. And so what I want to talk about next is strategies that you can use for reducing the number of event handlers and functions that are hanging around in your application so that you can reduce the overall memory footprint and therefore improve your performance. So let's talk about kind of some of these strategies here. So I don't know about you guys, but all the time I'll do a query selector all, I'll grab a bunch of elements, got them in a nice array, I'll start looping through them. And as I loop through them, I'll just stamp out a kind of a duplicate of an event handler because that's really easy and convenient to do, right? But that creates a replica of your event handler for every single object in the collection. There's a better way to do this. There's got to be a better way. That better way is to use a single event handler and the magic of event bubbling, for all of your objects that are going to use a similar type of event handler. I'm kind of explained maybe a slightly different way. If I've got objects 1, 2, 3, 4, and 5, they've all got a common ancestor of the dude, right? And that dude, because of event bubbling, that dude ancestor receives all, let's call them click events from its children. And what you want to do is you want to place a single event handler on the dude and then use kind of event target to do detection to see which of the elements was clicked on, and then feed an argument back to your single event handler to modify it for there. And I know, again, this is not a decision that you would make for maintainability or code legibility, but it is absolutely one that you would make for optimized performance. Let's see what kind of a difference that actually makes here. So I'm going to bring up a nice little YouTube video here again. And I've got, let's see here. We're going to let this guy, we're actually going to fast forward a little bit here. All right. So in one of them, I've got a handler at the top, and another one, I've got a single event handler. Let's see here. One of them is a single event handler for all elements. One of them, it is a multiple event handlers, all pointing back to a common function. And then in the last one, it is a one-to-one mapping between object and event handler. And what I'm going to do is I'm kind of running through each of those three scenarios, and I'm taking a heap snapshot for each of those scenarios. So snapshot 1 was one event listener listening to all of them. Snapshot 2, got to take the heap snapshot there. It's calculating it up. And then snapshot 3 is going to be the multiple event handlers pointing back to one function. Take another snapshot. And what I want you guys to keep your eye on, as legible as it can be, is that right-hand column of the Chrome DevTools, there's a retained size. So for snapshot 3, that was multiple event handlers pointing back to one function. It's got about 257K that's in the retained size for that one. Snapshot 2, that was the one-to-one mapping between object and event handler. That's got 468K assigned to it. And snapshot 1, which is the one event handler for all objects, was back down to 257K as the heap snapshot. So a one-to-one mapping between event handler and object doubled our memory footprint and ultimately would kind of drain back kind of our performance potential, right? And in fact, here, as I expand it out, you can see all of those event handlers, one for each image element that I've got there. Let's make that real in terms of from how we see it, what it looks like from a code perspective. Going back to here. So that means from a code perspective, a bad here, this is where we've got that loop. We've got a single kind of loop that we're going through, and we're just stamping out almost the exact same function for every object in the collection. Super easy to read, easy to maintain code. I understand exactly what's going on here, but that's not the goal of today. The goal of today is to optimize for performance. Somewhat more difficult to read, but half of the memory footprint is for us to have a single parent that collects my one function, my one event handler, and then we have a little if statement. It could be a switch statement as well, but essentially we're using an internal statement to detect which object we're clicking on and then marshalling it out differently. Yeah?
Well, yeah, but of course with that example, it's kind of obvious that, I mean, you could call a function from within the loop, and I would say that you're already better.
But you still have an event handler at that point, even if we've got like equals click or add event listener click function e bracket go to single function close bracket, right? each one of those event handlers occupies additional memory. If it was, and to your point, I think this may have been what you were saying, if it was add event listener, click, common function, right? That's the third case that I was talking about, and both of those, the common function and the switch statement one, those have similar memory profiles, and I think that those work equally well. Does that, I see you wincing a little bit, so.
Yeah, but I think the path would be already better than mine. It might not be as good.
I totally agree. Drawing sharp contrasts, if you will. All right. So we're kind of here at the end of it. If you remember anything from today, it's like anyone can build shitty apps, right? You can do it. You can do it. You can do it. I know you've done it. Right? Anyone can build shitty apps. You don't have to. Just think ahead. Think ahead. Build for performance. Don't always favor kind of the easier thing to write. Think about how you're building it out. Yeah, if you guys want to kind of get in touch with me, I'd love to geek out with you about JavaScript, CSS, performance, any of that good kind of stuff. You can find me on Twitter at Ryan J. Salva. If you guys have been great about having conversations with me, let's also, we've got a good 5-7 minutes here. If you guys want to ask some questions kind of here at the end of it, I'd love to chit chat with you. Back there.
When you talk about a parent-child relationship, are you referring more to a has-a versus a is-a? Something that contains all of these rather than something that inherits from?
Yeah, so do you mean on the simple DOM versus complex DOM question, or on the event bubbling piece? The event handling piece. So the takeaway on the event handling piece, I guess, in order to take advantage of event bubbling, it has to be a has-a. They've got to be like direct ancestors of it. In order to take advantage of kind of like the principle of fewer event handlers in your application, parent-child relationship doesn't matter. The gentleman over here that had the suggestion of using add event listener, click, common function, that does not require a parent-child relationship and is nearly as effective as using the event bubbling technique. Adjacent to, yeah. I think what I heard you say is there a way, actually, can you repeat it? Okay, so I think what the question I heard was, is there a way to remove all event handlers that are associated with an object and just use a single function? Actually, was it really to a cleanup question? Or garbage collection? Other than looping through all the possible event handlers, I truthfully don't, maybe someone else knows offhand, no? Yeah, there's, not that I know of, so no remove all. Yep. All right, cool. Well, we'll call that it for today. Thank you guys so much. Truly appreciate the time.